one-to-one. It need not be that both sigma and tau are one-to-one. And for this we need examples. So I have this example with me. Let me just present it to you. Define sigma from this set into this set consisting of the three integers by what is the definition? 1 sigma is 1, okay, and 2 sigma is 2, and another function tau, we need one more. This one will be from 1, 2, 3 to 1, 2 by one tau is defined to be equal to 2, 2 tau is also defined to be equal to 2, and 3 tau is defined to be equal to 1. Okay. Note that sigma composition tau is both one-to-one and onto. So that means it satisfies both of these conditions. I mean, we are actually solving part A and B together. That's why we have not written anything here. So both one-to-one and onto, but sigma is not onto and tau is not one-to-one. So this one function, I mean this situation, this example consisting of these two functions, settle both the cases. And let us now see, I would like to end the solution here, but let us informally see using Venn diagrams that whatever we are saying is actually the case. When we take diagrams, it becomes very easy. We can see the whole situation at once. So sigma maps 1 to 1 and 2 to 2. That's all it needs to do, because there are only two elements in the domain of sigma. Excuse me. Okay, and for tau, what do we have? Tau maps both 1 and 2 onto 2, and it maps 3 onto 1. So this is our sigma, this is our tau. So from this diagram we can immediately see that sigma is not onto. because 3 is missing as an image, and tau is not 1 to 1 because tau maps both 1 and 2 to the same element 2. But what about sigma composition tau? You can see from here itself what sigma composition tau will be, but still let me just draw another diagram for you. You can just directly see that sigma composition tau will map this set into this set, which is actually the same thing. So it first takes 1 to 1 and then it takes that 1 to 2. So that means it is taking 1 to 2 and it is taking wait, I think I have made a mistake here. If I take 2 to 2, okay, let me just change the thing a little bit. Instead of mapping it to 2, let me just map 1 to 1. Let us define tau like that. So now in this modified form, tau is still not 1 to 1 because 1 and 3 are getting mapped onto 1 and sigma has not changed, so there is no problem with sigma. So now what sigma composition tau will do, it will first take us from this one to this one and then it will take us from this one to this one. So this is not the case. We will have this. Sigma composition tau will map 1 onto 1 and 2 onto 2. So you can see that sigma composition tau is both 1 to 1 and onto, but sigma is not onto and tau is not 1 to 1. So that's what that's how we completed the solution. Okay, now next we have this exercise number 10. Prove that there is a one-to-one correspondence between the set of integers and the set of rational numbers. See how much we have to write if we don't have symbols for these sets. Now in this solution I am going to use some results from analysis 1 by Terence Tao. Why I do that? You see, you probably already know how to show that these two sets are there is a one-to-one correspondence between them. These two sets have the same cardinality, in another language of saying the same thing, and that involves showing that the set of rational numbers is countable, although we have not defined what countable means yet, but you probably already know that. And you also may remember, if you know these things, then you also may remember that the proof will involve showing that a countable union of countable sets is countable and many other things. So we have to go through all those things, and we will go through all those things in analysis 1 by Tao. more formally, because here we don't have here we are here the treatment is somewhat informal. It's not absolutely formal. Like in Tau's analysis, we have come across axiomatic set theory and we are going through it. Here, however, we have seen that we only need naive set theory, but from a logical perspective, that is somewhat not that satisfying. So we will, since we will go through finite sets and everything else about set theory in an axiomatic format in Tau, so why not use those results here? So when we go to them, although we will be using them here prematurely, we haven't seen them yet, but they are available. We will see them in future when the time comes. So let us just use them here directly and finish the solution. That's all. We don't want to repeat things. So by corollary, (8, 1, 11) top. When I write something like this, you will have to understand that this is coming from analysis 1 by Tau. There is a volume 2, analysis 2, for which if we ever need some results from there, then to refer to such a result, I will develop some other notation. So this means analysis 1, and this says there is a one-to-one correspondence sigma from the set of integers into the set of natural numbers. It's not very difficult. This, in fact, we can show here itself. However, we choose not to. And by corollary 8, 1, 15, there is a one-to-one correspondence I need ink. Between the set of natural numbers and the set of rational numbers, which you already know we are denoting by this blackboard bold Q. Although we are still going to mention what they mean here. N, Z and Q denote the set of natural numbers the set of integers and the set of rational numbers respectively. Okay, now since we are using this result from Terence-Tao, and Terence-Tao has a slightly different meaning for this symbol, we have to mention that also. It should be kept in mind that in tau, n denotes the set which has the number 0, but for us we don't have. However, for us n means this set. Instead of writing however, let me just write but. However, this creates no problem because there is a one-to-one correspondence between the sets you can probably understand what this correspondence will be. If you don't, you take one mapping from this to this set, and the mapping just maps every integer to the 1 by adding 1 to it. That is, the image of x is x plus 1, and you will see that that will create a one-to-one correspondence between these two sets. To keep that, to help you remember that, I will write this. See the function or see the mapping, since we are using mapping. See the mapping tau in the solution to exercise 8C. We are writing it under a bracket, no? And inside that we have another vector. So this is okay. Okay, so that's why, hence, so we had one mapping from sigma from the set of integers into the set of natural numbers, and one mapping tau from the set of natural numbers into the set of rational numbers. So their composition will give us a mapping from the set of integers into the set of rational numbers, and since both of them are one-to-one correspondences, so the composition will also be a one-to-one correspondence. So hence sigma composition tau from the integers into the rational numbers is a one-to-one correspondence. Okay. Now you may be thinking that what these corollaries that we have stated here actually state. The first one is very easy. It just states that the set of integers is countable. That thing has been proved in the corollary. It comes as a corollary to some theorem. And the other corollary, the second corollary, just states that the set of rational numbers is countable. So that amounts to having a bijective mapping or one-to-one correspondence between these sets and the set of natural numbers. Okay, and this ends this solution. We then have exercise 11. If sigma maps S into T and A is a subset of S, the restriction, this is something new, may not be new to many of you, but new in this book. The restriction of sigma to A which is denoted by this symbol. We write A as a suffix of sigma, is defined by A sigma A. It is by definition equal to the same thing as A sigma. So this is a new mapping because this mapping has A as its first set or domain instead of S. So what we are doing is we are just restricting the mapping sigma, or a figure will help. This is S, this is T, and we have sigma. Now there is a subset A of S. If instead of applying sigma on the whole set S, you apply it on a subset, you will then have a mapping from A to T, and that mapping is the restriction of sigma to S. So here the only thing we change is the domain. The definition of the function, or the formula for the function, rather I should say, remains the same. Okay, so that is called the restriction. Its opposite is extension. If we have a function defined on a set and then you have a superset and you define another function whose restriction becomes this given function, then the other function becomes an extension of the given function. It's just the opposite thing. It's like superset and subset, one in relation to the other. If A is a subset of B, then B is a superset of A. If sigma is a restriction of tau, then tau is an extension of sigma. It's just a way of saying the same thing. Okay, so it's defined by this. For any he writes same meaning, any A belonging to A. Now there are three things to prove which are very easy, but nevertheless we have to prove them. Sigma A, first of all we need to make sure that this defines a legitimate mapping of A into T. Then in part B we have to, there are 3 parts. Sigma A is 1-to-1 if sigma is, that means the restriction of any 1-to-1 function is also a 1-to-1 function. However, the converse is not necessarily true. Sigma A may very well be 1-to-1 even if sigma is not. Okay. So let us now see the solution. Although parts A and B are almost trivial, but I am going to write the solutions because it's so trivial that sometimes triviality is confusing. It makes you believe that something is true because it seems obvious, but there may be many things lying underneath about which you may not guess at first glance. So you look at trivialities with as much rigorousness as you can for at least once, and then once you know that it is true and you have seen why it is true, then you can just treat that as a fact. Okay, so we have to we have to say that sigma defines the mapping of A into T for any A belonging to A, right? We have a unique A sigma belonging to T. Why is this true? It is coming from the fact that sigma is a well-defined mapping. So for any element in S, there is a unique image of that element under sigma. This statement can be said not for all elements in S, but in particular for all elements in A, in the subset. That there also the statement is true. So here you are getting that for every element in A, there is a unique A sigma in T. However, by the definition of this mapping, sigma A, which is being called the restriction of sigma to A sigma is nothing but the image of A under sigma A. Since A sigma A is equal to A sigma for every A belonging to A, sigma A is a well-defined mapping The author has not mentioned well-definedness. However, whenever we see the word mapping being used, it is a well-defined mapping. Of A into T. Okay, then next we have to prove that if sigma is 1-to-1, then so is sigma A. So we make our assumption. I wrote assumption. Assume sigma is 1-to-1. Then for any elements S1, S2 belonging to S, we have S1 not equal to S2 implies S1 sigma is not equal to S2 sigma. That's what being one-to-one means. In particular, now this is true, this implication is true for any elements S1 and S2 in S. In particular, if you restrict these elements in A, then also this will be true because A is a subset of S. In particular, for any S1 and S2 belonging to A, we still have that implication. This implies, however, when our elements are in capital A, then S1 sigma is nothing but the image of S1 under sigma A also by this definition, and S2 sigma is S2 sigma A. This implies S1 not equal to S2 implies, so this implication is being implied by the previous implication. S1 sigma A is not equal to S2 sigma A for any S1 and S2 belonging to A, and that just tells us that sigma A is one-to-one. Hence, and lastly, we have to show by an example, obviously, that we can have a one-to-one mapping sigma A that is not coming from a one-to-one mapping sigma. Although I may ask you to supply this example for me, but let me just write it for you. For S equal to T equal to this set, and A equal to 2, 3, sigma mapping S into T such that 1 sigma is defined to be equal to 2 sigma, which is defined to be equal to 1, and 3 sigma is defined to be equal to 2. Sigma A is one-to-one, but sigma is not one-to-one. So we just mention it like that. We can see why that is the case using a diagram, but I decide to not make it a part of the solution since that is too easy. So this is our S and this is our T and this is A. And what is sigma? Sigma maps both 1 and 2 onto 1, and it maps 3 onto 2. So you can see that this is sigma and the inner one is sigma A. You can understand this mapping, which is like this. sigma is not one-to-one. Sigma is also not onto, but we are not bothered about onto-ness here. Sigma is not one-to-one because sigma maps both 1 and 2 to that same element 1. However, the restriction of sigma on this subset is 1-to-1. It has different images for different elements 2 and 3. That's what you see we have written here. Different elements have different images. That's what one-to-one means. Okay, and the solution ends here. So this is the situation. Okay, after this we have exercise 12. This one is also pretty easy. If sigma maps S into itself and A is a subset of S such that there is a condition A sigma. Do you remember this set? This is the image of the entire domain under sigma. That is, in other words, it is the set of all possible images. Sometimes we also call this set the image set of the mapping. This is a subset of A. Prove that